January 20, 2016. The California Institute of Technology, Pasadena. Two astronomers are sitting on a finding that has taken them more than a year to fully trust. Not because the mathematics is uncertain. The mathematics is precise, reproducible, and has survived every internal check they have run against it. But because what the mathematics is pointing toward is so large, so close, and so consequential that publishing it without being certain would be the kind of mistake that defines and ends a scientific career. Konstantin Batygin is a young theorist in his early 30s. Mike Brown is in his mid-40s, already well known in planetary science as the person whose discoveries in the outer solar system played a central role in Pluto's reclassification as a dwarf planet a decade earlier. Between them, they have spent the better part of 2 years running orbital simulations, checking for systematic biases in the observational data, consulting with colleagues under confidentiality, and asking themselves the same question repeatedly. Is there another way to explain this? They have not found one. What they have found, what the simulations keep confirming from every starting point and every parameter variation they try, is that 6 objects in the outermost region of the solar system, beyond the orbit of Neptune, are moving in a pattern that has a probability of occurring by chance, on their analysis, of roughly 0.007%, 0.007%. These 6 objects, small, icy bodies in the scattered region beyond the main Kuiper belt, have orbits that are clustered, not randomly distributed, as they should be if nothing were influencing them. Clustered in both the orientation of their orbital planes and the direction of their closest approach to the Sun. Aligned in a way that, if you drew their orbits on a diagram, would look almost deliberate, pointed, collectively, in the same direction. Like 6 compass needles, all pointing at something that isn't on the map. The simulation tells them what could be pointing those needles: a planet, most likely around 5 to 10 times the mass of Earth, by the analysis Batygin and Brown publish, in a highly elongated orbit that takes it somewhere between roughly 400 and 800 astronomical units from the Sun at its farthest point. So distant that a full orbit takes between 10 and 20,000 years to complete. So far from the Sun that its surface would be near the temperature of empty space. So far that the sunlight reaching it is hundreds of thousands of times fainter than what reaches Earth. A planet that has never been directly observed, never been photographed, never been confirmed by any telescope. But a planet whose gravitational signature, whose fingerprint on the orbits of the objects it would have been herding for billions of years, is, in their analysis, the most parsimonious explanation for what the data shows. The paper is submitted to the Astronomical Journal on January 20, 2016. The title is careful and precise. Evidence for a distant giant planet in the solar system. The abstract does not claim discovery. It claims evidence, mathematical, gravitational, orbital evidence for the existence of a planet that has not yet been seen. Within days, every major science news outlet in the world is covering it. Within weeks, amateur and professional astronomers on 6 continents are pointing their telescopes at the regions of sky the paper identifies as the most probable locations. It is worth pausing on the asymmetry of that moment. The paper itself was a careful, technical document, full of orbital diagrams, statistical tests, sensitivity analyses, and explicit acknowledgement of uncertainty. The coverage that followed was, almost universally, none of those things. Headlines announced a 9th planet. Cable news segments showed artists' impressions of a dramatically lit world looming in the dark. Social media filled with confident pronouncements about a discovery that the paper itself had not claimed. The gap between what the paper said and what the public conversation said it said was wide from day one. And that gap repeated and amplified by every subsequent paper on the subject, has been one of the genuine difficulties of communicating the actual scientific state of the Planet 9 question. The paper said, evidence, much of the world heard, found. Throughout this video, we will try to use the language the science uses, not the language the headlines used. That difference is not a small one. And within the planetary science community, a debate begins that is, nearly a decade later, still ongoing. A debate that has, in the years since 2016, only deepened and intensified as new evidence has accumulated, as new objections have been raised and partially answered, as new theoretical frameworks have been developed and tested, and as new instruments, finally, have come online that may settle the question one way or the other within just a few years. The question of whether our solar system has a ninth planet, a hidden giant orbiting in the cold darkness far beyond Neptune, has gone from a fringe speculation to one of the most rigorously contested and consequential open questions in modern planetary science. And the evidence, almost a decade later, has not weakened. It has grown, but it has also become more complicated in ways that the original paper's neat statistical story did not anticipate. New surveys have found objects that fit the pattern. New surveys have found objects that don't. Different teams, applying different statistical methods to overlapping samples, have reached different conclusions about how strong the clustering signal really is. Alternative explanations have been proposed, tested, and partially accommodated. And, in 2025, for the first time, possible infrared candidates that may or may not be Planet 9 itself have begun to appear in the literature. This video is about all of that, not about whether Planet 9 is real in the sense that requires direct detection to confirm. We will be honest about the fact that it has not been directly detected and may or may not be in the next few years, but about the evidence that has accumulated since 2016 for its existence, about what that evidence actually says and what it doesn't, about the alternative explanations that have been proposed and how they have held up, about the surprising new candidates that have emerged in recent infrared analyses, and about what the discovery of Planet 9, if it is confirmed, would mean for our understanding of how the solar system formed and where it is going. The central tension of this story is specific and striking. The solar system has been studied with modern instruments for decades. We have mapped the surfaces of Mars and Venus, orbited Jupiter and Saturn, flown past Neptune, landed on comets, and detected planets orbiting stars hundreds of light years away. The idea that something 5 to 10 times the mass of Earth is sitting undetected in our own solar system, that our cosmic backyard contains a major planet we have never confirmed, seems, on its face, implausible. And yet, the orbital clustering that Badajian and Brown identified in 2016 has not gone away. Some of it survives careful corrections for observational bias, some of it does not. New objects have been found whose orbits deepen the clustering signal. Other objects have been found whose orbits weaken it. Theoretical mechanisms have been identified that explain how Planet 9, if real, would produce the observed patterns, and other mechanisms have been identified that might produce similar patterns without a planet at all. The statistical argument, refined over nearly a decade of analysis and debate, has not converged on a single answer. It has converged on a sharper question. By the end of this video, you will understand what the orbital clustering evidence actually shows and why it has not been easily dismissed in either direction. You will understand what Planet 9 is theorized to be, where it is theorized to be, and why it has not been directly confirmed yet. You will understand the strongest alternative explanations and how they compare to the Planet 9 hypothesis. And you will understand what discovery, or definitive non-discovery, would look like, what it would take to confirm or rule out a planet in the outer solar system, and what the Vera C. Rubin Observatory, which has just begun its scientific operations in Chile, is expected to do to this question in the next few years. We stay in the evidence. We follow the orbital mechanics. We represent the genuine uncertainty where it exists, and it is genuinely substantial, while being honest about why the evidence has accumulated the weight that it has. If rigorous, data-driven space science is what you're here for, subscribe to Galaxy Pulse before we go further. Every video follows the evidence, not the headline. Now, back to the outer solar system. To understand why the orbital clustering that Batajan and Brown identified in 2016 was not immediately dismissed as an observational artifact or a statistical fluke. Why it generated the response it did within the planetary science community. We need to understand the region of the solar system where it was found, and what the objects there are supposed to be doing. Beyond Neptune, at a distance of approximately 30 astronomical units from the Sun, begins one of the most structurally complex and least understood regions of the solar system. 1 astronomical unit is the average distance from Earth to the Sun, approximately 150 million kilometers. Neptune orbits at 30 the Kuiper belt, the ring of icy bodies that extends from approximately 30 to 50 contains hundreds of thousands of objects, ranging from small irregular chunks of rock and ice to dwarf planets like Pluto and Eris. These objects are the remnants of the material that the outer solar system's planet formation process did not incorporate into the major planets. The leftovers of the solar system's construction, preserved in the cold of the outer solar system for 4-5 billion years. It is worth dwelling for a moment on what these distances actually mean, because the numbers are so large that the mind tends to flatten them into a very far away, without registering the structure. Light, which crosses Earth's orbital radius in about 8 minutes, takes more than 4 hours to reach Neptune from the Sun. It takes nearly 7 hours to reach the inner edge of the Kuiper belt. If Planet 9 sits at the predicted 5 to 600 from the Sun, light from the Sun takes between 3 and 4 days to reach it, and another 3 to 4 days to bounce back to us. We are not talking about a slightly more distant neighborhood. We are talking about a region where the basic light crossing time of the local geometry is measured in days, and where the Sun, viewed from out there, would not look like a sun at all in the familiar sense. It would be a single very bright star among many, with no visible disk to the naked eye, hardly distinguishable from the brightest objects in the sky. Beyond the Kuiper belt, the picture becomes less certain and more remarkable. The scattered disk, a population of objects with highly elongated orbits that carry them far beyond the Kuiper belt at their most distant points, extends to several hundred from the Sun. And beyond that, theoretical models predict the existence of the Oort cloud, a vast, spherical shell of icy bodies extending to perhaps 100,000 from the Sun. The reservoir that supplies the long-period comets that occasionally fall inward toward the inner solar system. The objects in these outer regions are not well characterized. Thousands have been identified and had their orbits measured with reasonable precision. Almost certainly hundreds of thousands more are too faint to have been detected by current surveys. They are small, typically at most a few hundred kilometers across for the named ones, far smaller for the majority of the population. They are dark. They are cold. And they are, in the context of standard models of solar system formation and dynamical evolution, supposed to have orbits distributed in a roughly random fashion, some elongated, some more circular, pointing in various directions with no strong preferred orientation. This is the expectation. The outer solar system's small body population, disturbed and scattered by the gravitational influence of the giant planets over billions of years, should look, from a statistical perspective, like a fairly isotropic distribution. No strong clustering, no preferred direction, just the slowly dispersing remnants of formation, orbiting in the cold and dark at the edge of the solar system. Think of it this way. Imagine you have a large field, enormous, extending beyond sight in every direction. You scatter 1,000 coins randomly across this field. If you come back years later and find that 50 of those coins have rolled to within a few meters of each other, all pointing the same direction, you do not assume that the coins rolled that way randomly. You assume something was there, a slope, a groove in the ground, some structure in the field that directed them, or, alternatively, that you only happened to look in certain parts of the field, and the apparent clustering reflects the spotlight of your attention rather than a real feature of the coins. The outer solar system's most distant objects are the coins. The clustering, to the extent it is real, is the thing that shouldn't be there. The bias debate is the question of whether the spotlight, not the slope, is what produced the appearance. Here is what the outer solar system's most distant objects are supposed to look like in terms of orbital distribution. The argument of perihelion, the technical term for the orbital parameter that describes which direction an object's closest approach to the Sun is pointing, should be distributed randomly among the objects in the outer solar system. If you measure this parameter for a large sample of objects and plot it, you should get a distribution that is roughly uniform. Some objects pointing in every direction, no strong preference for any particular orientation. What Badigian and Brown found when they analyzed the 6 most distant known objects in the scattered disk, objects with perihelia beyond 30 and orbital periods of thousands of years, was not a uniform distribution. The arguments of perihelion for these 6 objects were clustered within a roughly 100-degree range, when, on a random distribution, they should have been spread across the full 360 degrees. The orbits were aligned, but the clustering is not just in one parameter. The orbital planes of these objects are also clustered. They are tilted in the same general direction relative to the solar system's mean plane. And, most remarkably, the clustering in both parameters points the object's orbits in a way that is roughly anti-aligned with the direction of the hypothesized planet. This is exactly what the gravitational influence of a large, distant planet would produce. It would shepherd smaller objects into stable orbital configurations that are anti-aligned with its own orbit, a dynamical mechanism that orbital mechanics analysis confirms is physically realistic. The probability of this clustering occurring by chance, in the sample of 6 objects Badigian and Brown analyzed, was estimated at roughly 0.007%, a statistical significance that the paper calculated and that has been the subject of vigorous methodological debate ever since. That number, while striking, deserves a little context. A 0.007% probability sounds like vanishingly small odds, and it is, on its face. But statistical significance in astronomy comes with several layers of qualification that are easy to miss in headline coverage. First, the figure depends on what you treat as the null hypothesis. If you assume the underlying population is perfectly uniform and ask how likely it is that 6 randomly drawn objects would look this clustered, you get a small number. If you allow for the possibility that the underlying population itself has some clustering for reasons other than a planet, say, from formation processes, the relevant comparison changes. Second, statistical significance is meaningful only as long as you account for every way the result could have arisen, including how you happened to pick those 6 objects in the first place. If the surveys that found them preferentially looked in directions where clustered objects would be visible, the apparent clustering may partly reflect the selection rather than the underlying truth. None of these qualifications make the original number wrong. They make it the start of a longer conversation rather than the end of one. That longer conversation is exactly what the field has been having ever since. That is the gap between the random distribution the outer solar system should show and the clustered, aligned distribution that the original analysis found. That gap is what the Planet 9 hypothesis was proposed to explain. Let's be specific about what the 6 original objects in the Badajian-Brown analysis were, because the specificity matters. The objects are formally classified as extreme trans-Neptunian objects. ETNO, a category defined by having a semi-major axis greater than 150 O and a perihelion greater than 30 O, placing them beyond Neptune's gravitational influence at their closest approach. At the time of the 2016 paper, the 6 objects used in the analysis included Sedna, 2012 VP113, 2004 VN112, 2010 GB174, 2013 RF98, and 2007 TG422. Each of these objects is remarkable in its own right. Sedna, discovered by Mike Brown's group in 2003, has a perihelion of approximately 76 O and an aphelion estimated at roughly 900 O. An orbit so elongated that it takes around 11,400 years to complete one revolution around the Sun. Its existence was puzzling from the moment of its discovery, because standard models of solar system formation had no clean mechanism for placing an object in an orbit that never comes close enough to Neptune to have been gravitationally scattered there. Sedna required an explanation that went beyond the standard dynamical model, and Planet 9, once the hypothesis was on the table, was one of the explanations that worked. The initial skeptical response to the 2016 paper focused on a specific concern: observational bias. The objects in the outer solar system are discovered by telescope surveys, and surveys are not uniformly sensitive across the sky. If the surveys that discovered these 6 objects happen to have preferentially looked in certain directions, certain regions of sky that were better positioned for observation due to telescope scheduling, weather, or the geometric layout of survey fields, then the apparent clustering could reflect bias in where the surveys looked, not a real clustering in the underlying population. This is a legitimate concern. Observational bias is one of the most persistent sources of spurious results in astronomical survey science. Badajian and Brown addressed it in the original paper, arguing that the degree of clustering they observed was too strong to be explained by the known biases. Subsequent analyses by independent groups reached different conclusions, some supporting the bias argument, some finding that the clustering survived bias corrections. The debate over observational bias has been the central methodological argument about Planet 9 since 2016. It has not been fully resolved. What has happened in the years since the original paper is that the dataset has grown significantly, and the debate about what the larger dataset shows has deepened the scientific engagement with the question rather than resolving it cleanly. The honest summary is that the original 0.007% figure does not survive every rigorous bias correction unchanged, but neither does the clustering disappear entirely under any rigorous bias correction. Something is in the data. The question is exactly how much of it is signal and how much is the shape of where we looked. This kind of slow, contested methodological argument is the part of science that tends to be invisible to outside observers. The popular impression of how science works is that researchers run an experiment, get a result, and publish it. The reality is that, for questions at the edge of what current instruments can resolve, much of the actual work is the years-long negotiation between groups about how to correctly handle the limits of those instruments. Whose bias model is right, which corrections are too conservative, which too aggressive, which statistical framework is best suited to a sample this small with errors this complicated. These are not glamorous questions, and they do not produce dramatic papers. But they are exactly the questions that decide whether a borderline result is a real discovery or a phantom of the analysis pipeline. The Planet 9 debate has, more than most recent astronomical controversies, been a public showcase of this kind of dispute. The next generation of survey data, well characterized, large, and homogeneously processed, is what the field is waiting for to move past this argument and into a clearer signal. The mechanism by which Planet 9, if it exists, would produce the observed orbital clustering is well understood in the framework of orbital mechanics. It is worth explaining precisely, because the mechanism's specificity is part of what makes the hypothesis testable. When a small body, an ETNO, passes through the outer solar system on its elongated orbit, it spends most of its time at its most distant point, near aphelion. This is simply because orbital velocity is slowest at aphelion. Objects in highly elongated orbits spend most of their orbital period near the farthest point, where they are moving most slowly, and relatively little time near the Sun, where they are moving fastest. A large, distant planet, like the hypothesized Planet 9, would gravitationally interact with these objects primarily during the long periods when they are near their aphelia, the slow, distant part of their orbits. These gravitational interactions are individually weak. The planet is far away, the objects are small, and the interactions occur over very long timescales. But they are cumulative, over millions to billions of years. The repeated, slow gravitational nudges from a Planet 9 would gradually organize the orbits of small bodies into preferred configurations. The specific configuration that results, the anti-alignment of perihelia with Planet 9's position, the clustering of orbital planes, is a consequence of a dynamical mechanism called secular resonance. Objects, in particular, orbital configurations, relative to Planet 9 experience gravitational tugs that systematically shift their orbital parameters in correlated ways. Objects in the wrong configuration gradually have their orbits disrupted and are either scattered out of the region or sent on different trajectories. What remains, after the billions of years of orbital evolution, is a population with a specific, coherent orbital structure. This is not a mechanism invented to explain the observations. It is a well-established result from orbital mechanics that applies wherever a large body influences smaller ones over long timescales. The same kind of mechanism operates in the asteroid belt, where Jupiter's gravity creates the Kirkwood gaps, regions where the asteroid density drops sharply because objects there are in resonances with Jupiter that destabilize their orbits over time. The physics is the same, the scale is different. To appreciate why this matters for the credibility of the hypothesis, it helps to recognize that the Planet 9 model is not unique in postulating an unseen body to explain orbital regularities. The history of celestial mechanics is, in a real sense, the history of exactly this kind of inference. When the orbit of Uranus was found to deviate from what Newton's laws predicted given the known planets, the mathematician Urbain Le Verrier calculated where an unseen body would have to be to produce the discrepancy, and Neptune was found, within a degree of where his calculations said it should be, less than a year later. When the orbits of stars near the center of our galaxy were found to be tracing tight ellipses around something invisible, the mathematics pointed to a supermassive black hole long before any direct image of one was made. When galaxies were found rotating faster at their edges than the visible mass could account for, the inference of dark matter was, and remains, the dominant explanation. None of these inferences was uncontroversial in its time. All of them were criticized for postulating unseen things to save the appearances. Some, like Neptune, were dramatically confirmed. Others, like Vulcan, the planet once hypothesized to explain Mercury's anomalous orbit, which turned out to be explained by general relativity instead, were dramatically refuted. The Planet 9 hypothesis sits in this tradition. It might be right, It might be the next Vulcan. The method itself is sound. The verdict depends on what the data ultimately shows. The specificity of the predicted orbital configuration, anti-alignment with Planet 9, clustering in the same orbital plane, is what makes the hypothesis falsifiable. If Planet 9 exists in the location, and with the orbital parameters that the models predict, the clustering pattern it produces should have specific, detailed properties that can be checked against the observed population. As the dataset grows, the constraints on the hypothesis tighten. Here is where the Planet 9 hypothesis connects to questions larger than orbital mechanics. If Planet 9 exists, if our solar system contains, say, a 5 to 10 Earth mass planet in a highly elongated orbit at hundreds of astronomical units from the Sun, then our understanding of how the solar system formed and evolved needs to accommodate it. Current models of solar system formation, the NICE model and its successors, describe a solar system that formed from a protoplanetary disk, with the 4 giant planets Jupiter, Saturn, Uranus, Neptune, forming relatively close to the Sun, and then migrating outward over hundreds of millions of years through gravitational interactions with each other and with the disk. In these models, the outer solar system's small body populations, the Kuiper belt, the scattered disk, the Oort cloud, acquired their current orbital distributions as a result of this giant planet migration. Where would Planet 9 have come from? In the context of these formation models, the leading hypothesis is that Planet 9 formed in the inner outer solar system, perhaps as a 5th giant planet core, competing for material with Jupiter, Saturn, Uranus, and Neptune, and was gravitationally ejected outward by a close encounter with one of those planets during the period of giant planet migration, rather than being ejected from the solar system entirely, which would be the fate of most objects experiencing such an encounter. Planet 9, on this hypothesis, was thrown into a highly elongated but still bound orbit that kept it gravitationally tied to the Sun at its closest approach while carrying it to enormous distances at its farthest. This kind of scenario is not exotic in modern planetary science. It is, in fact, becoming increasingly clear from observations of other planetary systems that violent early instabilities are common. Many stars host wide-orbit giant planets at distances of tens to hundreds of distances at which planets are not thought to be able to form in place, because the protoplanetary disks from which they grow are not dense enough that far out. Those planets must have formed closer in and migrated outward, either smoothly or, in many cases, dramatically through encounters with other planets in the same system. The list of free-floating planets, worlds that have been ejected entirely from their original star systems and now drift through the galaxy without a parent star, is also growing as infrared surveys become more sensitive. The dynamics that could have placed a Planet 9 in our own solar system are dynamics that are clearly operating elsewhere in the galaxy. Our solar system would not be unusual for hosting such an object. If anything, the absence of such an object would be slightly more unusual than its presence. This scenario has been modeled and is consistent with the formation models. The probability of any individual planet being ejected to a stable, bound orbit rather than escaping the solar system entirely is low, on the order of a few %, but not negligible, and with the number of planetary embryos competing in the early solar system's giant planet region, the probability of at least one being retained in a distant orbit is reasonable. The alternative origin hypothesis, that Planet 9 was captured from another star system during the Sun's early cluster environment, when stars were close enough for planetary exchange to occur, is also theoretically viable and has been modeled. Both formation scenarios predict a Planet 9 with the general characteristics that the orbital clustering evidence suggests. A massive body in a distant, elongated orbit. They differ in their predictions for the composition and detailed orbital properties of the planet. A captured planet might have a different inclination distribution from an ejected one, which means that, if Planet 9 is found, the details of its orbit and properties may eventually tell us which formation pathway it followed. That, in turn, would be informative about the early dynamical history of the solar system, in ways that no other available evidence could be. If Planet 9 is confirmed, it will be the first direct evidence that the solar system's current architecture is the result of a violent early history in which a planet was either ejected from the inner regions or captured from elsewhere. Evidence that the solar system we live in today is not the solar system that originally formed, but a modified version shaped by early dynamical instability. The 6 original objects were just the beginning. Because, in the years following the 2016 paper, the search for more extreme trans-Neptunian objects, objects that would either strengthen or weaken the clustering signal, produced a dataset that has changed the terms of the debate in ways the original paper's authors did not fully anticipate. The 2016 Badigian-Brown paper was based on 6 extreme trans-Neptunian objects. In the years since publication, systematic surveys of the outer solar system have identified dozens more ETNO, each one adding a data point to the clustering analysis and either strengthening or weakening the statistical case for Planet 9. The most significant survey contribution in the years immediately following the 2016 paper came from the Outer Solar System Origins Survey, OSOS, a Canadian-led telescope program specifically designed to study the trans-Neptunian object population with carefully characterized observational biases. OSOS was, in the context of the Planet 9 debate, a critical test. It was one of the first surveys with sufficiently well-documented pointing history and detection efficiency to rigorously correct for observational bias in the ETNO sample. The initial OSOS analysis, published in 2017, produced a result that the Planet 9 advocates found uncomfortable. After applying bias corrections, the OSOS team concluded that the clustering signal in their carefully characterized sample was substantially weaker than the Badigian-Brown analysis had suggested. Their conclusion: the apparent clustering in the original 6 objects could plausibly be explained, at least in significant part, by observational bias rather than a real physical alignment. This was a serious challenge. The OSOS team was rigorous, their bias characterization was thorough, and their statistical methodology was sound. Badigian and Brown responded by arguing that the OSOS sample was too small, only a handful of qualifying objects, to either confirm or refute the clustering definitively, and that the bias corrections the OSOS team applied were overly conservative. The methodological debate continues in the literature, with different groups reaching different conclusions about how much of the clustering survives rigorous bias correction. What happened next, however, added complexity to the debate in a direction that the pure bias explanation had difficulty fully accommodating. The Dark Energy Survey, a Southern Hemisphere imaging survey primarily designed to study cosmological questions, serendipitously discovered a number of trans-Neptunian objects in the course of its wide-field observations. When the DES Trans-Neptunian Object Catalog was published, it contained hundreds of new TNO detections, including a number of objects in the extreme orbital category. The DES team analyzed their sample for clustering signals, with their own careful bias corrections. Their finding: a statistically significant clustering in one of the orbital parameters they examined that was not easily explained by observational bias in their survey. The DES survey covered a specific region of sky, and the clustering they found was not aligned with their survey footprint in a way that would be expected if the signal were purely a bias artifact. The DES result did not resolve the debate. It added a new data point that the bias-only explanation needs to account for. The clustering detected by DES is not identical to the clustering in the original Badajian-Brown sample, and the relationship between the two signals is a subject of ongoing theoretical analysis. As of the most recent published analyses, the total sample of ETNO with well-characterized orbits has grown to several dozen objects. The clustering signal, corrected for known biases in various ways by various groups, ranges from a marginally significant to highly significant, depending on the methodology applied. The honest summary of the current state. There is something in the data that requires explanation. Whether that something is a real physical alignment of orbits pointing toward a large, unseen perturber, an artifact of survey incompleteness and bias, or some combination, remains genuinely contested. What the dataset growth has done that is unambiguous, it has made the question testable in ways it wasn't in 2016. More objects means more constraints on the models. The specific orbital parameters of each new ETNO either fit the Planet 9 prediction, or they don't. And several of the most recently discovered extreme objects, including objects found in the last few years by surveys targeting the regions of sky where Planet 9 is predicted to have the strongest influence, have orbits that fit the Planet 9 model reasonably well, while others, including a notable 2025 discovery, do not. Beyond the orbital clustering of ETNO, a separate and independently compelling line of evidence for Planet 9 comes from a different category of anomalous objects. Bodies whose orbits are so unusual that standard solar system dynamics, even accounting for the 4 known giant planets, cannot easily explain how they got there. The most prominent member of this category is Sedna. Sedna's orbit is genuinely puzzling independent of any Planet 9 hypothesis. Its perihelion, its closest approach to the Sun, is approximately 76.0. This is important because 76.0 is far enough from Neptune that Neptune's gravity cannot have scattered Sedna to its current orbit. The standard scattering mechanism that places objects in the scattered disk requires close encounters with Neptune. Objects that come within roughly 30-35.0 of Neptune can be gravitationally kicked onto more distant, elongated orbits. Sedna never comes closer than 76.0 to the Sun. It is essentially unreachable by Neptune's scattering influence. It is worth recognizing how rare this configuration is. Most known trans-Neptunian objects, whether they are well-behaved members of the Kuiper belt or members of the scattered disk on their wandering elliptical paths, have orbits that bring them close enough to Neptune at some point in their long histories that the giant planet's gravity is plausibly responsible for shaping them. Sedna is in a different category, a category whose existence requires a different physical story. When Mike Brown's group discovered Sedna in 2003, they recognized immediately that they had found something whose presence in the solar system the standard models did not account for. It was not just that Sedna's orbit was unusual. It was that no available mechanism in the late solar system could have placed it there. Either something that no longer operates today shaped its orbit long ago, or something still operating shaped it more recently. That choice, historical mechanism versus active mechanism, is part of what makes Sedna scientifically interesting. The Planet 9 hypothesis chooses the second branch, an active mechanism that is shaping the outer solar system right now, of which Sedna is one product among several. Standard models of solar system formation had no clean mechanism for placing Sedna in its current orbit when it was discovered in 2003. Several alternative mechanisms were proposed. A close stellar flyby in the Sun's early cluster environment that could have perturbed objects outward. The gravitational influence of the protoplanetary disks' outer regions during the Sun's formation, or the gravitational influence of another star in the Sun's birth cluster. All of these mechanisms are viable in principle, but they are historical. They operated in the first few 100 million years of the solar system's history and no longer apply today. Planet 9, if real, would provide a currently active mechanism. Models of its dynamical influence show that, in the predicted parameter range, it can actively produce Sedna-like objects by lifting the perihelia of objects that are initially in closer, Neptune-scattered orbits, pushing their perihelia outward through secular gravitational interactions into the detached zone where Sedna lives. In 2014, before the Badigan-Brown paper was published, Chadwick Trujillo and Scott Shepard discovered a second Sedna-like object, 2012 VP-113. Its perihelion is approximately 80°, similar to Sedna's, and similarly unexplainable by Neptune scattering alone. The existence of a second Sedna-like object strengthened the case that the detached population was not a statistical fluke, but a real class of objects requiring a physical explanation. Since 2016, several more objects with Sedna-like or extreme properties have been found. Each one either fits or doesn't fit the Planet 9 prediction for where such objects should be found, given the hypothesized planet's orbit. The picture they collectively paint is mixed, but, on balance, not yet inconsistent with the hypothesis. And then, in 2025, a discovery genuinely complicated this picture in a useful, scientifically productive way. A team, led by Sihao Cheng at the Institute for Advanced Study, announced the discovery of a new extreme trans-Neptunian object, designated 2017 of 2-1. With an exceptionally distant orbit. Its perihelion is far from Neptune, its aphelion is hundreds of O. It is, in scale, the kind of object the Planet 9 story would naturally describe. But its orbital orientation does not match the Planet 9 clustering pattern. It is, in the language of the field, a wild card. A Sedna-like object whose existence does not fit the shepherded pattern that Planet 9 is supposed to produce. This is not necessarily a fatal problem for the hypothesis. Cheng and collaborators noted that Planet 9's gravity would, over billions of years, be expected to disrupt such an object, unless 2017 of 2-1 only recently wandered into the region, nudged by passing stars or the galactic tide. But it is the kind of finding that requires the Planet 9 model to do more work. Either the hypothesis must account for some exceptions among the most extreme objects, or it must explain where 2017 of 2-1 came from and why its orbit looks the way it does. Discoveries like this are exactly what a healthy hypothesis testing process looks like. A model makes predictions, observations are made, some confirm and some challenge, and the model either accommodates the challenges or is revised. Scientific credibility requires engaging seriously with alternatives to the preferred hypothesis. And the Planet 9 hypothesis has generated a productive set of alternative explanations that have been rigorously tested. The first, and most important alternative, is the observational bias explanation, which we have already discussed. Its current status, viable, but, in most analyses, insufficient as a complete explanation. The bias argument can account for some of the apparent clustering. It has more difficulty accounting for the DES result, which used a survey with different and partially independent biases. And it does not by itself explain the existence of individual anomalous objects like Sedna and 2012 VP-113. The bias alternative remains in play as a partial explanation, but it is not widely accepted as the complete explanation for all of the phenomena that Planet 9 was invoked to address. To see why bias is such a persistent concern, it helps to picture how outer solar system discoveries actually happen. A survey telescope is scheduled to observe certain patches of sky on certain nights, under certain conditions. Some of those choices are driven by science requirements. Others, by weather, by competing observation programs, by the geometry of where the telescope can point at a given time of year. Over years and decades, the accumulated coverage map of the sky is uneven. Some patches are imaged many times in many filters, others are imaged rarely or never. An object that happens to lie in a well-covered patch is more likely to be found than one in a poorly covered patch, even if the underlying population is uniform. This uneven coverage can create the appearance of clustering even when there is none, simply because the discovered objects reflect where the surveys looked rather than where the objects actually are. Correcting for this bias requires modeling, for every survey contributing to the sample, exactly which patches of sky it covered, to what depth, and how its detection efficiency varied across those patches. That modeling is genuinely hard, and the different conclusions reached by different groups largely come down to different choices about how to do that modeling. The second alternative, proposed by Anne-Marie Madigan and colleagues at the University of Colorado in 2018, is called the collective gravity hypothesis. This proposal suggests that the orbital clustering could be produced not by a single large planet, but by the collective gravitational self-interaction of a large population of small bodies in the outer solar system. If the scattered disk contains significantly more mass than current surveys suggest, perhaps several Earth masses of material in objects too small and too distant to have been individually detected. The mutual gravitational influence of this population could, over billions of years, produce the orbital alignments observed without requiring a single large perturber. This is a genuinely interesting hypothesis. It does not require an undetected planet. It requires an undetected population of small bodies, which is consistent with current survey incompleteness in the outer solar system. Madigan's group has published detailed simulations showing that collective gravity can produce clustering under certain conditions. It is also worth noting why this kind of alternative gets serious treatment. The history of physics is full of cases where what looked like the action of a single distinct object turned out to be the collective effect of many small ones, or vice versa. Brownian motion was originally puzzling because it looked random in a way that suggested some unknown driving force. It turned out to be the accumulated buffeting of invisible molecules. The galactic rotation curves that pointed to dark matter could, in principle, have been the result of modifications to gravity at large scales rather than an unseen substance, and that idea, modified Newtonian dynamics, has been seriously developed even though it remains a minority position. Hypothesis space, when an observation is genuinely puzzling, includes not just an unseen large thing, but a many small unseen things, and the laws themselves work differently here. All three are taken seriously by careful scientists. Only follow-up evidence decides between them. The challenges for collective gravity specifically. The hypothesis requires the outer solar system to contain significantly more mass than is consistent with some formation models. The specific orbital configurations it produces differ from the Planet 9 prediction in subtle but potentially testable ways. And it does not cleanly explain the existence of Sedna and 2012 VP-113 in their current orbits. The collective gravity mechanism operates differently from the perihelion raising mechanism that Planet 9 provides. The two hypotheses, Planet 9 and collective gravity, are not necessarily mutually exclusive. It is possible that both a large distant planet and a more massive than expected small body population contribute to the observed orbital structure. The theoretical and observational work needed to disentangle their relative contributions is ongoing. A third alternative, proposed by several groups, is that the clustering is produced by the galactic tide, the gravitational influence of the Milky Way's disk on the outermost objects in the solar system. The galactic tide is a real and well-established influence on the Oort cloud, and it does affect the orbits of the most distant solar system objects. But the galactic tide's effect on objects with semi-major axes of a few hundred the range of the Etno in question, is generally considered too weak to produce the degree of clustering observed. This alternative is not widely considered viable as a complete explanation. A fourth alternative, proposed in various forms over the years, suggests that the clustering could be an artifact of the specific statistical methods used in the original analyses, and that properly accounting for the non-uniform prior distribution of orbital parameters would eliminate the statistical significance. This methodological challenge was responded to by Badigian and Brown in subsequent papers, and the debate over the correct statistical framework continues. Different groups, applying different methods to overlapping data, reach different conclusions about the significance level, a situation that reflects genuine methodological disagreement rather than fraud or error, and that will be resolved by a larger, better characterized dataset. The current state of the alternative explanations, none of them, individually or in combination, provides as complete and parsimonious an explanation for the full set of phenomena: the orbital clustering, the existence of Sedna-like objects, the highly inclined and retrograde orbits, the population of objects with extreme aphelion distances, as Planet 9 does. This does not prove Planet 9's existence. Parsimony is a guide, not a proof. But it does explain why the hypothesis has maintained scientific credibility and continued to attract serious theoretical and observational work nearly a decade after its proposal. In April 2024, Brown, Badigian, and colleagues published a paper that added a different kind of evidence to the case. Evidence based not on the most distant objects, but on a class of objects with low inclination orbits that reach into the inner solar system. Their analysis argued that the way certain trans-Neptunian objects make their way onto orbits crossing into Neptune's neighborhood is difficult to explain without a planet roughly in the predicted Planet 9 parameter range. This is a different kind of test from the original clustering argument. It uses a different population of objects, examines a different feature of their orbital evolution, and either confirms the hypothesis or it doesn't on its own terms. The 2024 analysis was, broadly, confirmatory, adding another independent line of indirect evidence to the case. This is what a maturing hypothesis testing process looks like. The original 2016 argument was based on a single statistical signature in a small sample. By the mid-2020s, the case rested on multiple independent lines of evidence. The clustering of extreme objects, the existence of detached Sedna-like objects, the existence of highly inclined and retrograde TNOs, and the dynamics of low-inclination objects with Neptune crossing perihelia. Each line is, by itself, suggestive but not conclusive. The accumulation of multiple independent suggestive findings is what has kept the hypothesis credible and active. Planet 9 has not been directly confirmed. This is the most powerful argument against its existence. If a planet 5 to 10 times the mass of Earth is somewhere in the outer solar system, why haven't we found it definitively yet? The answer lies in the combination of distance, size, and sky coverage. Based on the orbital mechanics models, Planet 9 is expected to be located somewhere between roughly 400 and 800 astronomical units from the Sun, with its most likely current distance estimated at around 500 to 600 astronomical units. At such extreme distances, Planet 9 would be incredibly faint in reflected sunlight. At a distance of 500 astronomical units, the amount of reflected light reaching Earth would be many orders of magnitude weaker than the light we receive from objects closer to us. Because of its great distance and very slow orbital motion, its apparent movement across the sky would be extremely small, only a few arcminutes per year. In a single image, it would appear almost identical to a distant background star. Detecting it requires either observing its slow movement by comparing images taken at different times, which is the standard method used to discover trans-Neptunian objects, or predicting its position accurately enough to perform a targeted search. Several searches have been carried out since 2016. One of the most comprehensive recent efforts was published in 2024 by Brown, Badigan, and Matthew Homan of the Center for Astrophysics. Their study used the extensive image archive of the Pan-STARRS survey on Haleakala, Hawaii, together with data from previous searches, to systematically eliminate Planet 9's presence across a large portion of the predicted search region. According to their analysis, approximately 3/4 of the most likely sky area has now been ruled out to a relatively bright magnitude limit. This is an important result. It suggests that if Planet 9 exists and has the expected brightness for its estimated size and distance, it is probably not located in the regions where most searches have focused. Instead, it may lie within the remaining quarter of the predicted search area, be fainter than the Pan-STARRS detection limit, occupy a less thoroughly surveyed region of the sky, or possess properties different from those originally assumed. It is worth understanding the logic of this kind of a ruling out work, because it is the unglamorous backbone of how a real search proceeds. When a telescope surveys a patch of sky to a known depth and does not see a target, that null result is not nothing. It is real information. It tells you that whatever you were looking for is either fainter than your survey could reach, or smaller, or in a different patch of sky, or not present at all. Combining many such null results over years, across many surveys, gradually carves the search volume into smaller and smaller pieces. After 9 years of this carving, what remains is a narrower region that has either not yet been searched to sufficient depth, or contains a planet whose properties differ from the standard assumptions. The carving is what makes the next major survey's job tractable. Instead of needing to search everywhere, the Rubin Observatory can prioritize the regions that have not been ruled out, deepening the search there with a sensitivity that earlier surveys could not match. This is the kind of progress that does not generate headlines but matters enormously. Each square degree of sky carefully ruled out is one more square degree where the planet, if it exists, is not. The search is converging, slowly, painfully, and methodically. And then, in 2025, the search took a turn that nobody had predicted. A team, led by Terry Long Fan at National Tsinghua University in Taiwan, working with colleagues including Tomitsugu Goto, published a paper in the publications of the Astronomical Society of Australia, describing a different approach to the problem. Instead of looking for Planet 9 in reflected visible light, they searched archival far-infrared all-sky surveys, where a cold but warmer than its surroundings planet would radiate its own thermal emission. They compared data from the ERAS satellite, which surveyed the sky in 1983, with data from the Akari satellite, which surveyed in 2006. A 23-year baseline, long enough that a planet at hundreds of should have moved across the sky by a measurable amount in that time, even if very slowly. The logic of the approach is worth pausing on, because it solves one of the central difficulties of the visible light searches. A planet at 5 or 600 reflects only a tiny fraction of the already faint sunlight that reaches it, and that reflected light is then diluted by another factor of distance squared on the way back to Earth. The numbers, on careful analysis, place the reflected light brightness near the edge of what even very large telescopes can detect, and far below what older wide-field surveys could capture. Infrared is different. A planet, several Earth masses in size, even at the cold temperatures of the outer solar system, has internal heat, some left over from formation, some from ongoing radioactive decay in its interior, and that heat radiates outward as thermal infrared. The planet does not depend on reflecting sunlight. It glows, faintly but detectably, on its own, for a body of the predicted mass at the predicted distance. This thermal glow falls within the sensitivity range of dedicated infrared surveys. The ERAS and Akari all-sky surveys, conducted decades apart, provide exactly the kind of long baseline comparison needed to look for the slow motion such a planet would show against an otherwise static background. What Fan and colleagues reported was striking. After modeling the expected brightness and motion of a planet 9 in the 7 to 17 Earth mass range at 5 to 7 and applying strict filters to remove known stars, galaxies, and other contaminants, they identified one strong candidate. A source whose position shift between the two surveys is broadly consistent with the expected motion of a planet in roughly the predicted Planet 9 region. A follow-up paper using Akari data in a different way by an overlapping group of researchers reported additional candidate detections. Sources whose half-year parallax motion within Akari's own observation cadence is consistent with what a body at Planet 9 distances would produce. None of these candidates has yet been confirmed by direct, follow-up optical observation. The signals could be Planet 9. They could also be uncatalogued background sources, transient infrared events, asteroids or comets that happen to be in the right place at the right time, or simply artifacts of how the data was processed across two satellites built decades apart. The authors themselves have been careful to note these possibilities and have explicitly called for follow-up observations by ground-based telescopes such as DE-CAM at the Blanco Telescope in Chile and by the Rubin Observatory to test whether the candidates are real. But the appearance of these candidates is the first time in the entire history of the Planet 9 hypothesis that specific objects with specific positions and motions have been proposed as direct detections rather than purely inferential signatures. Whether they survive follow-up will be one of the most closely watched questions in planetary science over the next year or two. If even one of them turns out to be Planet 9, the entire argument resolves. If they all turn out to be something else, the hypothesis remains in its current state, alive, contested, and waiting for the Rubin Observatory. It is also worth being entirely honest about what these infrared candidates do and don't mean for the bigger picture. They do not, on their own, confirm Planet 9. They are candidates, not detections. They may resolve into something mundane on closer look, but they do show that the search has moved into a new phase, from inferring an unseen planet purely from its effects on other bodies to identifying specific objects in archival data that might be the planet itself. That is the kind of methodological progress that, regardless of whether the specific candidates pan out, expands the toolkit for hunting distant solar system bodies in ways that will benefit the field even if Planet 9 itself turns out not to exist. The instrument most likely to settle this question, one way or the other, is the Vera C. Rubin Observatory, the new wide-field survey telescope on Cerro Pachon in the Chilean Andes that captured its official first light images in June 2025 and is now beginning the legacy survey of space and time, its 10-year program to image the entire visible southern sky every few nights. The Rubin Observatory's primary mirror is 4 meters in diameter. Its camera, the LSSD camera, contains 2 billion pixels arranged across a focal plane, the size of a small dinner plate, the largest digital camera ever constructed for astronomical use. It can image a sky area dozens of times larger than the full moon in a single exposure. And it is designed to image the entire visible southern sky, approximately 18,000 square degrees, every few nights, to a depth that will detect objects far fainter than any previous wide-field survey has reached. The survey will produce roughly 20 terabytes of raw data per night. an unprecedented volume that the observatory's data pipeline is built to process and search for moving objects in close to real time. For Planet 9, specifically, the Rubin Observatory's relevant capability is this. At a distance of 5.0, a planet several times the mass of Earth with a roughly Earth-like reflectivity would have an apparent magnitude somewhere around 22 to 25, at or below the threshold of most previous wide-field surveys, but within Rubin's reach. Rubin's single-visit limiting magnitude is approximately 24.5. Combining multiple visits to the same sky position reaches considerably deeper. Planet 9, at the distances and sizes currently predicted, is within Rubin's detection capability across most of the predicted parameter range. The survey strategy matters, however. Planet 9 moves slowly. Detecting it requires either comparing images taken months apart and finding an object that has moved, or using algorithms specifically designed to identify slow-moving objects against the background of stationary stars and galaxies. The Rubin Observatory's data processing pipeline includes trans-Neptunian object detection algorithms designed for exactly this type of slow-moving, distant object. The team behind the LSST Solar System Science collaboration has been preparing these algorithms for years, refining them against simulated data, testing them on archival surveys, and developing methods specifically tuned to catch objects moving at the very low angular speeds that distant planets and Kuiper belt objects produce. By the time the survey reaches its full cadence, the pipeline will be searching every patch of the southern sky every few nights for exactly this kind of signature. The byproduct of this search, even before any Planet 9 confirmation, will be transformative for the outer solar system on its own terms. Rubin is expected to discover, across its 10-year survey, tens of thousands of new trans-Neptunian objects, a roughly tenfold expansion of the current catalog. The bias characterization of the Rubin survey will be documented from the beginning of operations, enabling rigorous correction for the observational effects that have complicated the analysis of previous surveys. This larger, bias-documented catalog will, by itself, dramatically improve the statistical case for or against the clustering signal, independent of whether Planet 9 itself is detected. Even in the scenario where Rubin does not find the planet, it will tell us, with much more confidence than we have today, whether the clustering is real and whether it requires a physical explanation at all. The timeline. Rubin's legacy survey of space and time is expected to formally begin in late 2025, with first-year science data accumulating through 2026, and the dataset expanding rapidly thereafter. Mike Brown himself has said publicly that, if Planet 9 exists with the properties his analyses predict, it is very possible that the Rubin Observatory will find it within the first year or two of the survey. Other astronomers, including some who are more skeptical of the hypothesis, agree that whichever way the question goes, Rubin will likely settle it within the first few years. This is, in the language of science, a sharp test. The hypothesis has specific predictions, the instrument has known sensitivity and sky coverage, the timeline is bounded. The ambiguity that has surrounded this question for nearly a decade has a defined endpoint somewhere in the next few years. There is also another possibility that the 2024-2025 period has put on the table. That whatever is shaping the outer solar system is not Planet 9 specifically, but something else, a different planet, in a different orbit, with different properties, that the orbital evidence is pointing at obliquely. In October 2025, a team including Amir Suraj and others published a paper proposing a smaller hypothetical planet, informally dubbed Planet Y, based on a subtle warping of the Kuiper belt's inclination distribution. Their proposed planet, if real, would be different from Planet 9. Closer, smaller, with a less elongated orbit. The hypothesis is preliminary. The evidence is much thinner than the case for Planet 9, and it may not survive scrutiny. But the appearance of multiple competing hypotheses, each based on different statistical features of the outer solar system, is itself informative. The data is rich enough that thoughtful people are reading different patterns in it. The Rubin Observatory will, in time, sort that out as well. This is, in a sense, what a maturing question looks like. In 2016, there was essentially one specific hypothesis, Planet 9 in roughly the parameters Badigian and Brown predicted, being weighed against the null hypothesis of nothing. Today, there are multiple specific hypotheses, each making different predictions, being weighed against each other and against the null. That is progress, not confusion. It means the field has moved from, is there anything there? To, if there is something there, which of several possibilities best fits the data? The Rubin Observatory will not just test one hypothesis. It will test the whole tree of them, and the result, whichever way it lands, will be informative far beyond the question of whether one specific predicted planet exists at one specific predicted location. There is a particular quality to the search for Planet 9 that is different from most astronomical searches. We are not looking for something arbitrarily distant or arbitrarily faint. We are looking for something in our own solar system, in the neighborhood defined by the Sun's gravitational dominion, that has been there, if it exists, for the entirety of the solar system's history, 4.5 billion years of existence, orbiting in the cold darkness beyond anything we have directly explored, gravitationally shaping the orbits of small icy bodies, the way a shepherd shapes the movement of a flock, silently, distantly, persistently. There is also something specifically humbling about that timescale, and it is worth letting it land. The solar system has been in, essentially, its current configuration since long before there were any creatures on Earth to look up at it. Whatever organizes the orbits of the outermost objects has been doing so for billions of years, through the entire history of life, through the rise and fall of continents, through every species that has ever lived and died on this planet. The patterns in the data are old. They were already old when single-celled organisms first appeared in Earth's oceans. They will still be there, doing whatever they do, long after our civilization has changed beyond recognition. The fact that we have only in the last few years learned to read them, that we are only now building the instruments capable of identifying their source, is a comment less on the patterns themselves than on us. A species that is just beginning to be able to perceive structures that have been hiding in plain sight at the edge of our own neighborhood since long before we existed. The solar system has always been the most immediate cosmic context for human existence. We have explored its planets by spacecraft. We have landed on the Moon, sent rovers to Mars, orbited Jupiter and Saturn. The idea that our immediate cosmic context contains something that we have not yet seen, something large, something massive, something whose gravitational influence has been operating on the solar system for billions of years, is simultaneously humbling and extraordinary. If Planet 9 is found, it will be the first major planet of our solar system discovered not by direct visual observation, but by the gravitational signature it leaves in the orbits of smaller bodies, a discovery by inference, by the slow accumulation of indirect evidence, by the mathematical patience of orbital mechanics. It will join a very short list of astronomical discoveries where something was inferred from theory before observation confirmed it. Neptune itself, discovered in 1846, based on the perturbations it caused in Uranus's orbit, is the most famous precedent. Planet 9, if confirmed, would be Neptune at a much greater distance, the same logical structure, the same inferential method, an enormous step further out. And there is a real possibility, finally worth naming, that the answer in the next few years will be neither a clean confirmation nor a clean refutation, but something in between. A planet of slightly different mass at a slightly different distance than predicted, or a different planet at a different location, or a confirmation that the clustering is real but produced by something other than a single planet. Science rarely resolves contested hypotheses into clean yes or no answers. More often, it resolves them into a yes, but with revisions, or no, but the question pointed at something genuine that needed a different answer. Whatever happens, the data that comes in over the next few years will turn the Planet 9 question into something more specific than it currently is. That is what good science does. It does not always give us the answer we expected. It almost always gives us a better question. After everything we have examined, the orbital clustering and the statistical significance, the anomalous existence of Sedna and the growing catalog of Sedna-like objects, the theoretical models and their predictions, the alternative explanations and their limitations, the surveys that have searched and ruled out large parts of the predicted region, the infrared candidates that may or may not be the planet itself, and the new survey instrument that is now turning toward the sky. Here is where the honest accounting stands. The evidence for Planet 9 is, in some respects, stronger than it was in 2016, and in other respects, more complicated. The dataset has grown. Some specific predictions of the Planet 9 model have been confirmed by new observations. Other discoveries, like 2017 of Tuhin 1, have complicated the picture. The alternative explanations have been tested and found to be incomplete on their own, but not entirely without merit. The hypothesis has survived nearly a decade of serious scientific scrutiny, and has, in 2025, produced its first specific direct detection candidates, which may resolve into the planet itself or into something else. It has not been confirmed. The planet has not been definitively found. It is worth being clear about what this means for someone watching from outside the field. The Planet 9 story is not a story of confirmation. It is also not a story of debunking. It is a story of a hypothesis that has held up well enough to remain the most discussed explanation for a real set of observations, but that has not crossed the threshold into established fact. Different careful scientists, looking at the same data, place the probability that Planet 9 exists somewhere between moderately likely and moderately unlikely, a range that itself tells you the honest state of the field. There is no consensus that the planet has been found. There is also no consensus that it does not exist. There is a question, sharp and ongoing, with multiple lines of evidence pointing in roughly the same direction, but none yet conclusive. That is exactly the kind of question that the next phase of observation is positioned to resolve. What the next few years, the first years of full Rubin observatory operations, combined with targeted follow-up of the infrared candidates, will do to this question is the most important near-term development in outer solar system science. The outcome will either find Planet 9, rule it out across most of the predicted parameter space, or force a significant revision of what the orbital evidence is telling us. But there is one thread in this story that connects Planet 9 to something even larger and stranger. If a planet of the predicted properties exists in the predicted orbit, its gravitational influence extends far enough to interact with the inner Oort cloud, the region where the long-period comets that occasionally fall inward toward the Sun originate. There is a related hypothesis, supported by a smaller and more speculative body of evidence, that Planet 9's orbital dynamics may periodically perturb Oort cloud objects onto Earth-crossing trajectories, that the most distant planet in our solar system, if it exists, may have a statistical fingerprint in the impact record of our own planet. The connection between the outer solar system's hidden architecture and the history of life on Earth is a story that goes much deeper than most coverage has reached. That one is next time. Tonight, we didn't just follow a hypothesis about an unseen planet. We followed the logic of orbital mechanics from a simple observation. 6 objects in the outer solar system, aligned in a direction they should not be aligned, to the most rigorous statistical and theoretical treatment of indirect gravitational evidence in modern planetary science. We traced nearly a decade of debate, the alternative explanations that were proposed and tested, the growing dataset of extreme trans-Neptunian objects that has complicated and deepened the picture, the survey that ruled out the planet from most of the predicted region, and the surprising infrared candidates that, in 2025, gave the search its first specific objects to follow up on. We sat with the genuine, carefully maintained uncertainty that the best researchers in this field hold about what the evidence is saying. Uncertainty that is not a failure of understanding, but a precise characterization of what the data can and cannot currently resolve. And we looked ahead at the instrument that is now beginning to image the sky, the Vera C. Rubin Observatory, in its first months of legacy survey operations, and understood that the era of ambiguity has a defined endpoint. The most powerful wide-field survey ever built is going to look at the region of sky where Planet 9 is predicted to be, to the brightness level where it should be detectable, and it will either find something or it won't. Both outcomes are scientifically transformative. Neither leaves the question where it is now. This is science functioning exactly as it should. A hypothesis with specific predictions, an instrument designed to test those predictions, a timeline that produces a result. The answer is coming. The question is whether we will recognize, when it arrives, the full weight of what it means. 3 questions that the current evidence does not answer. The first: is the orbital clustering real at the level required by the Planet 9 hypothesis, or can it be substantially explained by observational bias? This question will be answered by the Rubin Observatory's well-characterized, comprehensive survey, which will produce an ethnosample large enough and bias documented enough to settle the statistical debate. The second: if Planet 9 exists, what is its precise orbital configuration and current sky position? The models have narrowed the range, but not to a single point. The uncertainty in current sky position spans a significant arc. Finding the planet requires either luck in the early survey coverage, success of the infrared candidate follow-ups, or patience as the survey builds up the sky coverage needed to rule in or out the full predicted region. The third: if Planet 9 is not found, if the Rubin Observatory's 10-year survey concludes without a detection consistent with the predicted parameters, and the infrared candidates resolve into something other than the planet, what physical mechanism explains the orbital clustering and the existence of Sedna-like objects? This question is not one that goes away with a non-detection. It transforms into a search for an alternative explanation that must do all the explanatory work that Planet 9 currently does, without the convenience of a single large perturber. All 3 questions have a timeline. They are not indefinitely open. The Rubin Observatory data will accumulate. The statistical power of the ethno dataset will grow, and the constraints on all possible explanations will tighten. The resolution, confirmation, strong constraint, or surprising alternative is within the span of the next decade, and probably the first half of it. What the Planet 9 story teaches, approached honestly and without the distortions of either premature confirmation or reflexive skepticism, begins with the power of indirect evidence. The history of science contains many cases where something was inferred from its effects before it was directly observed. Neptune from Uranus's perturbations, black holes from the orbital dynamics of companion stars and gas, dark matter from galactic rotation curves. In each case, the indirect evidence was initially contested, alternative explanations were proposed and tested, and the eventual direct detection, where it has come, confirmed what the inference had already strongly suggested. Planet 9 is in this tradition. Whether it ultimately joins the confirmed column or not, the method, infer the unseen from the behavior of the seen, is one of science's most powerful tools. The second lesson is about the value of scientific patience. The orbital clustering of Etno was noticed because astronomers had been carefully cataloging objects in the outer solar system for decades, building a dataset, one difficult observation at a time, without necessarily expecting it to reveal a missing planet. The patience that built the Etno catalog is the same patience that makes datasets large enough to find subtle signals. Science that expects immediate, dramatic returns from each observation misses the discoveries that emerge only from the slow accumulation of unremarkable data points. It is also worth noting how unusual it is, in modern science, to have a question whose resolution depends on doing the same thing many times over many years, rather than on a single dramatic experiment. The Planet 9 story is fundamentally a survey story, a story about taking pictures of the same sky, night after night, year after year, and looking for things that move slightly. There is no eureka moment in that kind of work. There is only the slow building of evidence that, at some point, becomes either decisive or definitively absent. The third lesson is about genuine uncertainty and the temptation to resolve it prematurely. The public conversation about Planet 9 has repeatedly been driven by individual papers. One paper's result becomes, Planet 9 confirmed. The next paper's result becomes, Planet 9 debunked. When the scientific reality is a gradient of evidence that is moving slowly and unevenly toward resolution. Maintaining the genuine uncertainty, the honest acknowledgement that the hypothesis is well supported but unconfirmed, is harder and less satisfying than premature certainty in either direction. It is also more accurate. The fourth lesson is about the incompleteness of our maps. The solar system has been studied intensively for centuries, and the implicit assumption of most coverage is that its major features are known. Planet 9, if confirmed, would be the most significant revision to the solar system's known architecture in nearly 180 years, not because it was hidden by distance beyond current technology's reach, but because the combination of its distance, its slow motion, and the incomplete sky coverage of previous surveys placed it below the detection threshold of everything that came before the Rubin Observatory. The map is always more incomplete than it appears. The blank spaces are not evidence of emptiness. They are evidence of where we haven't yet looked with sufficient care. This same lesson applies beyond the solar system, and it is worth saying so explicitly. Exoplanet surveys over the past 2 decades have found that many planetary systems around other stars contain wide-orbit giant planets, objects at tens or hundreds of O, that may have formed through ejection processes similar to the one proposed for Planet 9. If our solar system is missing a wide-orbit planet, that would not make it unusual. It would make it more like the typical case observed around other stars. Conversely, if Rubin completes its survey without finding Planet 9, that result becomes evidence about our solar system's specific architecture, about why it might look different from the typical exoplanetary system. Either outcome is informative about a question much larger than just our own neighborhood. The local search for one missing planet is, in disguise, a test of how planetary systems in general are organized. And the fifth lesson is about the specific value of a question that is answerable. Many of the deepest questions in cosmology, the nature of dark matter, the cause of the accelerating expansion of the universe, the details of the very early universe, are questions where the answer, while perhaps approachable, is not on a defined timeline. Planet 9 is different. The instrument that will either find it or place the most powerful constraints ever placed on its existence is currently operating. The timeline is years, not generations. The question will be resolved within the scientific careers of the people who proposed it. That combination, a deep question, a powerful instrument, a defined timeline, is one of the most productive configurations that science can produce. What does it mean that the most immediate cosmic neighborhood, the solar system we have been studying with modern instruments for decades, may still contain a major planet that we have never confirmed? How does the Planet 9 story change how you think about the completeness of scientific knowledge, the difference between "we have looked" and "we have looked everywhere," with sufficient sensitivity, with full sky coverage? If Planet 9 is confirmed in the next few years, what does that validation of gravitational inference, of finding something real by following mathematics alone, tell us about the limits of what science can learn without direct observation? And if Planet 9 is not found, if the most powerful wide-field survey ever built completes its coverage of the predicted region and finds nothing, what does that tell us about the outer solar system, and about the question of what is organizing the most distant known objects into the pattern they show? If this story pulled at something, if the image of icy objects at the edge of the solar system pointing collectively at something the maps don't show, or the thought of a planet orbiting in darkness for 4.5 billion years while we searched for planets around other stars, or the appearance of specific infrared candidates that may finally let us follow up on a hypothesis that has lived almost a decade, kept turning in your mind, tell me in the comments. Which parts stayed with you? The statistics, the Rubin Observatory timeline, the infrared candidates, the thought of what confirmation would mean? And if you want more stories told this way, starting with the actual data, following the evidence through its complications and uncertainties, and not pretending to know more than the science does, subscribe to Galaxy Pulse. Every video on this channel is built on what the record actually shows. The full picture, every time. I'll see you in the next one. For nearly a decade, the mathematics has been pointing at something in the dark. 6 objects became dozens. The models became more specific. The predicted sky position narrowed. Most of the predicted region has been searched, and the planet ruled out from it. Specific infrared candidates have appeared, awaiting confirmation. And now, the most powerful survey instrument ever built is turning its 3.2 billion pixel eye toward the region of sky where the orbital mechanics says something large and cold and ancient may be completing its slow orbit around a sun so distant it barely registers as more than a bright star. The solar system we thought we knew may be missing something. The instrument that will tell us whether we were right to suspect it is now imaging the sky. And somewhere in those images, accumulating night by night, processed by algorithms designed for exactly this search, the answer may already be on its way to existing, waiting to be found in the data. There is a certain symmetry to this moment that is worth noting. Nearly 2 centuries ago, in 1846, a mathematician sat down with the orbit of Uranus and the laws of gravity and calculated where an unseen body would have to be to explain the discrepancies. Within a year, Neptune was found within a degree of the predicted location. The search for Planet 9 is a direct descendant of that calculation. The same logic applied to a different anomaly on a vastly larger scale, with vastly better instruments. The astronomers who did the original work in 2016 understood, when they published, that they were planting themselves in that lineage. They also understood that the planting alone is not the discovery. Leverrier did not find Neptune, the telescope at the Berlin Observatory did. The instrument that confirms or refutes Planet 9 will not be Mike Brown's or Konstantin Batagin's. It will be a survey telescope in Chile, processing data they will not even see in real time, applying algorithms that the field has been developing for decades. Discovery, in modern astronomy, is almost never an individual moment. It is the convergence of many people's patient work into a result that, when it arrives, will feel sudden, but will in fact have been a very long time coming. It is always the data, in the end, that decides. Galaxy Pulse, beyond the headlines, every single time.